Gnanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. So, we have the subject compiler design. As far as the previous episode is concerned, we have studied the there is a predictive parsing, that is table construction and predictive parsing. And as far as this episode is concerned, we are having that is one of the advantage of finding the predictive parsing table construction, that is to find out whether a given grammar is going to be an LL1 grammar or not. So, the grammar which you are giving for predictive parsing table construction is going to be the context free grammar, and we want to have the grammar that is an unambiguous grammar, and later we will be removing the left recursion available in the grammar, and then we will be removing the left factoring available in the grammar. But as far as the left recursion removal and left factoring removal are concerned, we have standard algorithms, so whose behavior are deterministic, and we will be able to remove the left recursion as well as left factoring. But whereas in the case of the ambiguity of the grammar is concerned, so we do not have any specific algorithm for removing the ambiguity available in the grammar. And because of if the grammar becomes very complex grammar, then removing the ambiguity is going to be an issue. Suppose if you do not remove the ambiguity, or if you are not aware that the grammar is an ambiguous grammar, so if you continue with the parsing table construction, so what will happen? So, we will be left with multiple entries available in the parsing table, that means in a cell. So, in the previous case, we have seen the predictive parsing table for the expression grammar, which we have constructed after eliminating the ambiguity, left recursion and left factoring. But if you go for constructing the predictive parsing for the parsing table for the same grammar, but before eliminating the ambiguity available in the grammar, then we will be left with some kind of parsing that is ambiguous, which means we will be having the parsing conflicts like shift reduce conflict or shift conflicts or reduce conflict. So, any one of this may happen if the grammar is having ambiguity. So, now how do you find out whether the table has multiple entries? So, we just leave it for that is constructing the table, and then after constructing the table we check whether we will be having multiple entries or not. So, if the table has multiple entries, then we will not be calling the grammar as LL1 grammar. So, if the grammar is not LL1, then we know that the parsing table will be having duplicate entries, and thus the parsing cannot be done in a deterministic fashion. This is one way of determining whether the grammar is going to be an LL1 grammar or not. Even we have there is a simple algorithm which will be used for finding whether the grammar is an LL1 grammar or not. So, we shall see that is how the given grammar is going to be determined, that is found by that is as whether it is going to be LL1 or not. So, here is the definition for LL1 grammar. So, first of all, the grammar G is going to be an LL1 if and only if. So, the first condition is we have the variable called A, for which there are two productions. One is A derives alpha and another one is A derives beta. So, if A derives alpha is a production or A derives beta is another production, then so we have three conditions here. The one is for no terminal A, do alpha and beta derive the strings belonging with A. That means alpha is certainly going to derive a string and beta is also going to derive a string, but both alpha and beta should not derive any string starting with the same terminal. That is the meaning of this first point. So, if you are having only one choice for the variable called A, then this is not at all an issue. We are going to do this job only when a variable has more than one production. So, A has more than one production, which is one is alpha, another one is beta. So, if both alpha and beta starts with a same terminal, or the strings derived from alpha and beta start with the same terminal, then the grammar may not be an LL1 grammar. The second condition is at most one of alpha and beta can derive empty string, that is both should not derive empty string. If both are deriving empty string, then we will be having the problem in that is expanding this A by whether it is by alpha or by beta. That is the reason why. So, if you want to have empty string, okay, no problem, but the empty string can be derivable from all, that is A by either by alpha or by beta, but not by both. That is second condition. And third condition is if beta is deriving epsilon, then alpha should not derive any string beginning with a terminal and follow of A. So, that is another thing. That is going to be vice versa. So, it can even be considered as if alpha derives empty string after one or more number of steps, then beta should not derive any string beginning with a terminal and follow of A. So, if these three conditions are satisfied, then we can call the grammar as LL1 grammar. So, this is one way of finding whether the grammar is LL1 grammar or not. The other way is we construct the predictive parsing table by using the usual procedure, that is constructing the first set, follow set, etc. And if there are multiple entries in any of the cell available in the predictive parsing table, then we will claim the grammar as a not LL1 grammar, and such a table cannot be used for parsing because of ambiguity available in the parsing action. It can be either a shift reduce conflict or shift shift conflict, or it can even be a reduce reduce conflict. So, now we shall see the other way, that is how we are determining whether a grammar is not LL1 or not. We have taken the grammar that is dangling else grammar. The dangling else grammar, we have already seen that it is used for generating the set of all if statements, and if the grammar is having ambiguity, it is actually because of the else which is hanging. So, we may not be able to know with what that is if or with what then part we will be that is associating the that is else part. So, this problem will be raised when we are having a non-matching, that is if and else. So, if all the statements, if statements are having both then part and else part, we will never be facing problem with your dangling else. If we are having the combination of ifs and thens or if statements such that some of the ifs are having only then component and some of them are having both then component and else component, and if they are nested together, there is a chance for misinterpreting with what that is if a particular else is to be associated. So, that is the ambiguity available in the grammar. So, now we are taking that grammar. So, the grammar is S derives ICTS, that is if condition then statement, or if condition then statement else statement, or any other statement which is not necessarily an if statement, and the condition can be some B. And we are not going for eliminating the ambiguity available in the grammar. So, we can even go for removing the ambiguity available in the grammar by that is classifying the productions into or the if statements into two. One is the matched if statements and another one is unmatched if statements. So, then we can say that the grammar is not having any ambiguity. But here we have taken this grammar to prove that this grammar is a not LL1 grammar. So, if you remove the ambiguity, then we go for constructing the predictive parsing table, means this grammar will be once again proved as a LL1 grammar. But as such, this grammar is having ambiguity and that is not going to be an LL1 grammar. So, we go for eliminating the left factoring and left recursion. We do not find any left recursion because all the right hand sides are starting with the terminals only, but left factoring is there. We find that ICTS and once again ICTS, there is a common factor. So, we will take it as alpha and we will produce it here. S derives, definitely the S must start with ICTS or it can even start with A. If it is any statement other than the if statement, we do not have any problem at all. So, if not, it must be ICTS, and for the connectivity reason, because it can even be an else also, we will introduce S prime. So, that is going to be S prime here, and S prime. So, the remaining from first alternate and remaining from the second alternate. From the second one we find ES is remaining, and from the first one we find there is empty. So, S dash is ES or epsilon, and as usual we are having the there is statement, there is a production for C which is going to be B. So, this is what the grammar, resulting grammar after removing left recursion and left factoring. So, now look at the way in which we are constructing the first set and follow set, which is mandatory for the table construction. We have the grammar after eliminating the left factoring. The first set of S is this I and A, and as far as S dash is concerned, it is going to be E and the epsilon, and for C is concerned, it is going to be B. And when you look at the follow set, so first you have to find out the that is the follow set of S is going to be dollar, and that is what we are having dollar in follow set of S, because it is going to be the statement terminator for any string derived from the start symbol of the grammar. And the next is by splitting this particular production, that is I, C, T, S and S dash. So, the first set of S dash minus epsilon is going to be in follow of S. First set of S dash is going to be E and a dollar, that is epsilon. After removing epsilon, we will be having E. So, as far as this particular production is concerned, we will be having E in follow of S. So, we are having E in follow of S, that is the first thing. And we can have one more split up. We take this T S S dash as your beta, and this is B. So, what will happen is the first of T S S dash is going to be T, that will be in follow of C. So, we are having follow of C with T. So, that is the rule number 2 application, it is all over. So, now when you go for the rule number 3, we say that the follow set of S is going to be in follow set of S dash. The follow set of S is going to be follow set of S dash. So, that is what we are having dollar and E here. So, even if you are repeating it for any number of times, we know that finally we will be having the same set, that is your first of S is IA, and first of S dash is epsilon comma E, and first of C is B, and the follow set of S is dollar and E, follow set of S dash is dollar and E, and follow set of C is going to be T. After constructing the first set and follow set, we can go for constructing the predictive parsing table. We know the predictive parsing table construction algorithm. We are having two number of rules. One is for handling the right hand side where we do not have any epsilon, and another one is for handling the that is a table the productions where we are having that is epsilon. So, by using those two rules, we will be able to come up with the predictive parsing table here. We are having 3 variables S, S dash and C, and terminals, 5 number of terminals from the grammar. Another the explicit one, it is going to be the dollar, which is denoting the that is the end of the string. So, because of S derives A is a production, we are having S derives A here, and we are having another one S derives that is I, C, T, that is S dash. So, this is going to be a production available here since not in S dash. So, we will be having the, so this production is supposed to be here, and the other one is going to be C derives B. So, we are having C derives B, and it is going to be there in the intersection called C derives B. So, this is what directly being obtained. S derives A is there, we giving you S comma A, and S derives I, C, T, S dash will give you this entry. So, that is what here, and now we are having the rule number that is 2. So, when we are having epsilon on the that is the right hand side, so what should be done? So, we are having there is only one rule, S dash derives epsilon. So, for that we have to find out the follow set of S dash. So, we know the follow set of S dash as dollar and E. So, the follow set of S dash is, since it is going to be dollar and E, so we will be having there is 2 places, the entry is called S dash derives epsilon and S dash derives epsilon. That is S dash derives epsilon will be written in E and dollar. So, now we find that we have S dash derives ES is a production and S dash derives epsilon is a production. and both the productions are there in the intersection called S dash derives E. So, if there is a need for looking at this during the parsing of F statement by this particular parsing table, and if you go for an intersection called S dash comma E, so what will happen is we will be left with two possible actions. If it is S dash derives E comma S, sorry E S, then it is equivalent to a shift action, and if it is S dash derives epsilon, it is equivalent to a reduce action. So, that is the reason why we find there is ambiguity in this there is grammar, and the ambiguity is creating multiple entries in the predictive parsing table, and because of the multiple entries in the predictive parsing table, this grammar will not be a useful grammar for parsing. That is, a string cannot be deterministically parsed by using this particular grammar. So, if it is the case, we will go for calling the grammar as an there is going to be a not LL1 grammar. So, that is the definition. Two cases, one is going to be directly using the formula, that is procedure, or you can construct the predictive parsing table, and we may say that it is going to be the grammar is not LL1 by using the predictive parsing table. So, we shall go for a short break, and after that we shall study the shift reduce parsing. Welcome back. We have seen the LL1 grammar, and we have seen the procedure for how we are declaring a grammar is not LL1 by constructing the predictive parsing table, which produces multiple entries in at least one of the cell. So, now we shall see that is the bottom up parsers. The parsers can be either top down or bottom up. The top down cases we have already seen two number of parsers, one is the predictive parser and another one is the recursive descent parser. And now we are going for one of the very simple parsing technique, which is coming under the bottom up parsing, which is called as the shift reduce parsing. The name itself is saying that it has two actions, one is the shift action, another one is going to be the reduce action. So, it is constructing the parse tree in a bottom up fashion, that is we will start with the leaf node and we will continue further, and that is towards the root, and once all the terminals from the buffer have been processed, and if you are in the there is parse tree construction with only one root node, only one node which is a variable, then we can say that the parse tree construction has been over and the parsing is over. As far as this parser is concerned, it is going to start with, or it is attempting to construct the parse tree from bottom to top, that is from leaf nodes to the root, and it is works by constructing the rightmost derivation in reverse. As far as the predictive parser is concerned, we know that it is going to be the leftmost derivation utilization, but whereas here it is going to be the rightmost derivation. We have a very simple grammar here, that is S derives A, AC, then B, E, and there are two rules for A, B or B, and one rule for B, it is going to be D. And now we have a string that is A, B, B, C, D, E, and let us see that is how it is going to be parsed as far as this particular grammar is concerned. I said it is going to be the rightmost derivation. So, we will be having the string here, we have the string that is A, B, B, C, D, E, and then we are having the next sequential form. So, this is the last sequential form, and S is the first sequential form if you are constructing the rightmost derivation, and we have the outcome of the rightmost derivation, that is nothing but the sequential forms, but in the reverse order. The first sequential form is S, the second one, third one, fourth one and fifth one. Now, we are having everything in the reverse order, A, B, B, C, D, E, and what happens here is this sequential form and this sequential form are differing in the shadowed region. So, we have a B here, and now it is being replaced as A. That means, this B is replaced by capital A, or this B is reduced to capital A by using the production called A derives B. And the second one, what happens here is A, capital A, then B, C, D, E. This capital A, B is reduced to capital A. It is because of another production called A derives AB. And next what happens is, we have a D and this D has been replaced by capital B. So, because of the rule B derives D. So, next what is happening here is A, capital A, C, B, E and the whole thing is reduced to S. So, this are the entire steps. So, we started with the sequential form. Here all these are leaf nodes. A, B, B, C, D, E are all leaf nodes and we are progressing towards the parent nodes. So, what happens is this B is replaced by A. So, B's parent is going to be capital A and next one this capital A and the small b are reduced to capital A. So, for both capital A and this B their parent is going to be capital A. Then for D the parent is going to be B and for A, capital A, C, capital B and E for all of them the parent will be S. So, that is going to be the root node and it is because of all these production rules A derives B, A derives AB and B derives D and S derives AA, C, BD, B and E. So, this is the entire process which has been described with a very simple example. So, now we should know what are the what is the meaning of handle and what is the meaning of handle pruning and what is going to be the canonical reduction sequence. As far as shifted list parsing is concerned, I already said that it is using the rightmost derivation and the rightmost derivation is used in the reverse to find out the parsing process or constructing the your parse tree from bottom to top. In every step of the sentential form, that is to get the previous sentential form, what should be done is you have to find out a substring and the substring from the sentential form is obtained. So, it has to be available on the right hand side of a production, that is first condition, and then sometimes we may have multiple number of substrings eligible for reduction. So, there is a need for remembering what is the position where you find out the substring which is to be replaced. So, whenever we define a handle, we should define two things. One is going to be what is the substring and the second one is going to be what is the position where the substring can be found. So, handle now it is defined as it is going to be some string called gamma, that is the right sentential, we are handle of a right sentential form, that is we are defining the handles only in the right sentential forms and the right sentential form is gamma. The handle is going to be your beta provided there should be a rule called A derives beta and the beta may be found in a position called P. So, now what will happen is, so we will claim this beta as the handle because of this beta is found at a position and it is replaced by A to get the previous sentential form. I repeat it, that is a handle in right sentential form gamma is a production of A for the form A derives beta and it is found in a position some P and now we are finding this beta, it is replaced by the left hand side A to produce the previous right sentential form in the rightmost derivation of this gamma. So, here what happens is, if you are having the sentential form, that is S derives in some number of steps alpha A W, then in the next immediate step we will be having alpha then beta W. Since it is going to be a rightmost derivation, we should know that the right hand side of this A which has been just expanded should not have any variable. That is the reason why we mark this as W, which is a notation used for denoting only terminals, and this A has been now replaced by beta. So, alpha A W is expanded to alpha beta W and then we will be calling A derives beta in the position following alpha is a handle of alpha, beta and W, and already I said that W contains only terminals. So, that is what the meaning of your handle. So, now the process of handle pruning is, so this is actually handle can be found in there is every sentential form. So, we go for that is finding handle in every sequential form and replacing it by the corresponding left hand side to produce the previous sequential form. So, the process of reducing the given string W to the start symbol of the grammar. How? It is by locating the handle and replacing it by the left hand side of the production and do it in a consecutive manner, successive manner, and finally we will be having the start symbol of the grammar on the root. So, this process is called the handle pruning, and what it will give? It is giving you the reverse of the rightmost derivation, and we call the sequence as this canonical reduction sequence. So, we start with the rightmost derivation, and the rightmost derivation will be taken, that is the outcome of the rightmost derivation will be taken in the reverse order, which we call it as the right sequential forms. And the right sequential form, in every step we find that what is getting reduced, and whatever is getting reduced, it is called the that is handle, and the continuous reduction process is called handle, and that is pruning, and the reduction sequence is called canonical reduction sequence. So, all these things are happening as far as shift reduce parsing is concerned. We shall take another example, that is we shall see how we parse the string, that is id plus id star, that is id here. The first step is you construct the rightmost derivation for the string, that is id plus id star id. So, we expand e, we know that this is an ambiguous grammar, but with an intention to derive the string id plus id star id, we go for the appropriate rightmost derivation. It is e derives e plus e and e plus e star e by expanding the rightmost variable, and here the rightmost variable e has been expanded by id, and the rightmost variable is now this, and now the rightmost variable is going to be this e. So, finally, we are having e derives id plus id star id. So, here is the handle pruning process, and we are having the right sequential form here. This is the first sequential form, and we have written everything in the reverse order. So, the last sequential form is id1 plus id2 multiplied by id3. So, what is the handle here? The handle here is id1, here is the handle. The reducing production is, that is going to be e derives id, and which has been used to get the next sequential form. It is going to be e plus id star id, and the next step once again id, the reducing production is e derives id, and next step once again id, the reducing production is e derives id, and here we have the sequential form called e star e, and that is going to be the right hand side of a production called e derives e star e, which has been replaced, and now we are having e plus e, and e plus e itself is available in the right hand side of a production called e, and that is reduced to this. So, actually what these are all meaning? So, everything is going to be a pointer to a node in the parse tree. id1 is a node in the parse tree, plus is a node, id2 is a node, star is a node, and id3 is also a node. So, in the initial step of your parsing process, we are having only the that is forest, which means independent, that is trees are there. So, id1 is a tree, plus is a tree, id2 is a tree, star is a tree, and id3 is also a tree. In various stages, what happens is we will be combining the different trees to produce that is single tree. So, here we are having id1 reduced to e, id2 reduced to e, id3 reduced to e. So, now we find that this e, star and e, so these three pointers or node pointers are linked to this e as children. So, then they are having this e plus e. These three pointers are taken and linked with this e as their children. So, finally, we have only one pointer. So, this could be taken as the stack entry. So, this is what being happening here. We started with the empty stack, with completely we are having id1, id2, id3 etc. up to that is finally we are having the dollar, and continuously what will happen is we are having pointers. So, id1 is there, it is reduced to e, then e plus id2, and every time whatever we find on the stack, they are all the pointers. So, we continuously process leave nodes ID1, then ID2 and then ID3, and finally, we will be left with one symbol on the stack, which is nothing but the start symbol of the that is parse tree, and that is going to be the root. The start symbol and root must be same. This is what the process how we are generating the parse tree from the given sentence. The sentence given for you is ID1, ID plus ID2 multiplication ID3, and finally, we have left with nothing on the buffer, but we have only one node called root node on the stack. So, this is how we are parsing the string that is using the shift reduce parsing. So, to summarize, we have seen that how the given grammar is proved as not LL1 with the help of the constructing the predictive parsing table, and also we have seen that how the shift reduce parsing is used for constructing parse tree, but in a bottom up manner, that is using the Rice essential form, canonical reduction sequence, and the process called handle pruning. So, to see the questions, so the definition for LL1 grammar, and how do you prove a grammar is LL1, and how we parse the strings by using shift reduce parsing, what is the meaning of handle pruning, and what is the meaning of handles, but all this could be explained just by constructing the rightmost derivation for the given grammar. So, with this I complete this episode. Thank you all.